Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you're doing good. In this, we're gonna see maximum employee to be invited to a meeting. Company tags you can find on the website. Now, coming on that, it simply says that you are given. Basically, there's a company and it's organizing a meeting and it has list of n employees. As you can see, you are given n employees. Here, I have 4 employees named numbered from 0 to n-1. Now, they have arranged a large circular table capable of seating any number of employees, and again you can put up all n employees also on that specific table. It's a circular table, that is a fact. Now the employees are numbered from 0 to n-1 as we saw previously, and each employee has a favorite person that they will attend the meeting only if, again that's a very important point, only if they can sit next to their favorite person at the table. So as we can see, for 0 the favorite person is 2. For, again, when I say 0, which means the index, so for index 0 the favorite person is 2. Index 0 will sit only if he can find that okay 2 is there. For 1 the favorite person is 2. For 1 the favorite person is 2. For same way, for 2 the favorite person is 1. For 2 the favorite person is 1. So there is actually a directed link from one person to another, which means that for 2 he is okay to sit without 0, but 0 will not be okay without 2. So it is like you like your crush, but your crush doesn't like you. Same way, that is the reason it is a directed link. That is the reason I have to build a corresponding directed graph for it. Okay, let's continue. Now, ultimately, it says that the favorite person of an employee is not themselves, which means that there will not be any cycle. Like, it is not a self-obsessed person. No, they are kind of linked to each other. There will not be any single cycle. And also given a zero indexed array favorite where the favorite of I denotes the favorite person of the ith employee. As you can see, I have to return the maximum number of employees which I can invite to a meeting. Obviously, in this case, I can simply see that I have 0, then whose favorite is 2, then 2 whose favorite is 1, 1's favorite is 2, 3's favorite is 2. Now, if I plan, again, let's see whom, let's say I plan to invite. If I plan to invite 2, okay, if I plan to invite it 2, then obviously I have to invite 1, right? And if I invite 1, okay, I plan to invite 2 also. Okay, that is satisfied. If I plan to invite 2, that is okay. So far it is okay. But I still have 2 people left. Can I place them? Let's see. Let's try to also invite 0. If I try to invite 0, yes, he can come up. Why he can come up? Because 2 was like this. He has 2 vacant location. Every person, if they are sitting in a circular table, they have 2 vacant position. So one vacant position is filled by 1. I still have one vacant location, so obviously it can be filled by anyone. So let's say I filled it by 0. Okay, filled by 0. Then if let's say I plan to invite 3 also, then what 3 will say? 3 will say I want to sit beside 2. But obviously 2 only had 2 vacant locations, both are filled, so I cannot invite 3 now. What if I would have invited 3 rather than 0? Okay, it would have been similar way, because instead of 0 I would have placed a 3 here, and now 0 cannot be invited. So I just want the count. Count is at max I can invite 3 people. Again, these are the observations which you can easily see. So far the observation seems like that any node can have one outgoing edge only. Why it is the case? It is simply because I can say that one node is nothing but one person. So 0 as a person can only be at one index. That is the reason 0 can only go to 2. As in, like, for these are the persons. So these are persons which are indexes. Indexes are unique. That is the reason I can have only one outgoing edge from one specific person. Okay. Next observation which we can have is that any node can have at max 2 neighbors in final answer. So again, although if you will see, it is not at max, it will be actually exactly 2, because it is a circular table. But why I said at max, you will realize very easily. Why? Because even if let's say I would have placed a 3 here, although the condition was he just needs to sit beside 2, now he still has an empty location, and ultimately indirectly he is sitting beside 1. So that is the reason I told you that any neighbor can have at max 2 neighbor only. Okay, so these are the observation which we got from the first example. Let's go to the next one. Next one says, okay, 0 has, 0 has a favorite person as 1, 1 has a favorite person as 2, 2 has a favorite person as 0. Okay, so it is already in a cyclic fashion. So, okay, I'm good to go. So did you feel so far the kind of stuff which is involved? Okay, firstly we realize it is a directed graph. Then we realize that we have to deal with cycles in this graph. Again, not sure what to find, but deal with the cycles. And again, if you don't know, then to deal with the cycles in directed graph, we already know there is a very well-known algorithm. Again, if you don't know how to deal with cycles, I will link the video in the description. But okay, we have topological sort. We have also simple DFS, how we can deal with the cycles. But okay, no worries. Let's go to third example. Third example says that, again, this is the question and I have shown as form a directed graph. Now, let's try to sit the people here. Okay, let's make them sit. If I make them sit, let's say if I make 0 sit, if I make 0 sit, obviously 3 should be there. Okay, 3 is there. Let's say let's make it a bit above. Okay, if I made 0 sit, 3 should be there. Then if I made 3 sit, obviously 4 should be there. If I made 4 sit, 1 should be there. If I made 1 sit, 0 should be there. Okay, now if I ask you, all of these I have placed, can I place a 2 here? Now you might say, Aryan, not technically, like, because obviously if I try to place a 2 here, then I'm saying that 2 needs to come again. Like for 2 the neighbor would be 1. 1 already has 2 neighbors. I told you that a person can have only 2 neighbors. That is the reason any other person cannot attach with them. Which means, again, it gives us a hint that if I have a cycle, then any another person will not attach with them. But there is also one contrary thing which you just now saw. This is also a cycle, but now here the person can attach. Yes, here the people can attach, because if it is a cycle of length 2, it only indicates that things are dependent only on the one person. If the cycle goes beyond length 3, like 3 or maybe more than that, then it will say I already have 2 people along with me as a neighbor. That is the reason this condition actually says that for a cycle of length more than 2 only, you cannot attach anyone else. Let's try to see, if I attach anyone else, what will happen. Let's say, okay, I want to have a 2 here. Let's say, okay, imagine I want to have a 2. Imagine I want to have a 2. In that case, I will be having a 1. Okay, if I have a 1, I need to have a 0. Okay, if I have a 0, I need to have a 3. Okay, if I have a 3, I need to have a 4. Okay, if I have a 4, I need to have a 1. As I will try to have a 1, it will start violating, because I cannot have 3 neighbors to one node. It is a cycle, and again, when I say it is a circular table, one node, which means 1, can only sit beside 0, and 2, it cannot also sit beside 4. It is not a, like, that kind of table. So okay, what are the observations from this? Observation here is that obviously if I have a cycle, it can only occur, which means all these branches, they cannot occur. Only the cycle can occur. That is the thing. But again, I mentioned like no other branching can occur. But again, I also said that if a cycle is of length 2, then branches can occur. And again, we will see that obviously we will try to have at max one branch, because obviously if it is already a cycle, right, of length 2, then I can have one other extra branch. That's it. I cannot have 2 branches, because if I have 2 branches along with cycle, obviously I am screwed up. Okay, so this says that if there is a cycle of length more than 2, then no branching possible. But if there is a cycle of length equal to 2, then I can have a branching possible. Now, when I say branching is possible, then again, what will be the answer? So let's say this is a branching. Sorry, let's say this is a cycle of length 2. Again, I'm only talking about length 2 now, right? Because for length more than 2, only the cycle can come. There's no branching even possible in that case. And if I try to achieve the branching, which means even if this branch would have been very high length, still this is not possible to actually take the branch, because as I will start taking the branch, I would end up in an incorrect situation. So no matter how big the branch is, for a cycle of length more than 2, it is not possible to take it. Okay, coming on back, if I have a cycle of length 2 and I have multiple branches, okay, let's say this is the branch, 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 this is the branch. If that is the case, what should I do? Obviously, for this specific node, I can only take one more person. So which means I can take only one more branch. Obviously, as a human, I will say I will take the branch with the maximum length. Yes, I will take that length. So what I will do, I'll have to discard the other lengths. Okay, I'll discard the other lengths. Same way for this node also, I can take at max one more extra branch. So I'll take this one which has the maximum length. I will discard other branches. So technically what I did, I actually am taking the maximum length branch from any node. We will see how to calculate that, but logically this is what we are doing. Now there is one more thing that which is not covered in the example itself, is what if I have multiple cycles. What if I have multiple cycles, which means I have, let's say, one cycle here, one cycle here. Now the question is, like, if you have this cycle, obviously this is the graph which I have represented, but as a question you have to place the people on a circular node. So the question is, can you place them? Obviously you will try to say, let's try. Obviously you cannot take the branches, so branches is like already gone from one of the circular queue. So imagine that you have two circular queues only, like two circular graphs, directed graphs only. Then if I have already this, let's see, if I have 1 1 0 3 4, I've placed them already. These have two neighbors, all of them has two neighbors, and these also have two neighbors. But now I have to place these all together. Can I place them? Obviously not, because if I will try to place, let's say, 5 in this thing, what will happen? Obviously he has to come at either here or here or here or here or anywhere. As soon as it starts coming anywhere, it needs to come anywhere. So it has to say, okay, for one give me 3 neighbors, which is not possible. That is the reason, if I have a cycle of length 2, sorry, more than 2, I can only and only have one circular graph. Or even if they are multiple, then I have to take the one which has the maximum circular length, right? Let's say if there would have been 6, so like its length is 1 2 3 4 5 6, its length is 6. So imagine, yeah, let's say you have disconnected components. So if you have one of length 6, one of length 4, I will take the one with the maximum length, because I know I cannot take others. Okay, but this was the case when you had obviously a circular length of more than 2. But what if it is a 2? If it is a 2, obviously I know I can take the branches. As I take the branches, it will come down to the condition what we saw in the very beginning, that as you know that these were circular. This is one such branch. Obviously indirectly this is empty, his neighbor, there's no condition here, so I can simply attach it like this. If I attach it like this, obviously how the answer will become, that if I have a circular here, okay, sorry, this was one such length of circular length 2, another is here of circular length 2, again this is empty, again like there is no neighbor restriction here, so I can simply put these two as neighbors, I can simply put these two as neighbors. So how the graph will look like? Graph will look like, okay, the graph will start from here, 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 and this is the corresponding cycle. This is how in a circular fashion they can be placed. So we realize that if the cycle is of length 2, in that case I can take the corresponding maximum length branches, and if there are multiple such components which are doing this, I can attach these components also, because they will still have free ends which can be attached with one another component. Okay, so far with the observation which we have seen, the answer, obviously answer is nothing but the answer which we want, which is the maximum number of employees which we can actually seat or invite to the meeting. The answer will nothing be the single cycle of length more than 2. Again, if there are multiple cycle, just take the one having the maximum cycle length. Again, if it is more than 2, if it is equal to 2, then you will try to have the sum, again along with the extension, sum of all those components, which means this also along with the extension. Just count the cycle component along with the extension, simply add them. This can be other candidate. Now the very quick question which can come to your mind is, if you don't think that, is it always possible to get a cycle? Yes, it will be, because if you know that it is an array in which 0 1 2 3 4, these are the indexes and corresponding are the values are, okay, again anything from 0 to n minus 1. So if I have some edge here, some edge here, some edge here, some edge here, I need to, which means, let's say if I have a 1, let's say I have a 2, I have a 3, I have a 4. So it says, okay, 0, there's an edge to 1, 1 to 2, 2 to 3, 3 to 4. Now I cannot repeat a 4 here. I have to repeat something else. Now that something else can only be from 0 to 3. If I place any number, let's say 2, then obviously I'm breaking an edge to, like node 2. So I will ultimately form a cycle, which means, as you can see, if I just put it here, it will be 0, like 2 to 3, 3 to 4, and 4 to 2. So I will have a cycle no matter what, because I have only one outgoing edge and I have only these number of nodes. So this is your answer. Let's see. Now you got a logical idea. Let's see how you will find the actual values, because the prime thing here is finding the extension length and finding the cycle length. Now, if you don't know if it's a directed graph, you're talking about cycle, then there are two ways to solve it, either via simple DFS or via a Khan's algorithm. Khan's, like K-A-H-N-S algorithm. Now, the easiest one is BFS. If you don't know how to do it, just go and watch this video. That is the reason to solve the cycle length also. Again, this video tells to find a cycle, but actually, again, when I say find cycle, you can also know the cycle, its length, all that stuff you can easily know with the help of this intuition itself. But just to dry it, I will show you that how you can do it. Imagine that you have extensions, you have a cycle, and this is, and again, you can have multiple such components. So forget about that. But firstly, you realized that you have to actually get rid of these extensions and make sure that, okay, for this node, which is the maximum extension I can have. Although you might say, Aryan, because there's a cycle of length more than 2, so extensions would not be required. Yes, true, but it is just to explain in a general manner that how would you find the extension length and also the cycle length, right? This is the general example which I'm giving you. So what you will do, obviously you have to remove these extensions. What is the identity of this extension which can be removed? Obviously, if you look closely, these are the edge nodes, or I should say the nodes which have in degree as 0. So I can do one thing. I can start removing this in degree nodes and can try reducing it, and will simply store, okay, at this node the maximum depth here is 4. Although there is also a 3 here, but again I can only have 1, so I'll store a 4. Again, there are multiple variations of this problem. You might be asked to actually add it. In that case, just simply add it. But in this case, I want only the maximum one, so I will take the maximum one. How I will do it? I can simply firstly figure out the nodes having in degree of 0. So I have to maintain the in degree. That's one thing. As you can see, I have maintained the corresponding in degree. Then, as I maintain the in degree, I will simply start removing these nodes until I can remove it. How? Let's say if I remove this node, the next node neighbor in degree will become 0. He can also, again, when I remove it, I will simply make sure I am putting up the depth. So here the depth is 1. As I remove it, in degree becomes 0, but also the corresponding depth became a 2. His depth by default is 1. Again, by default is 1. Then when I remove this, I will make sure to maximize his in degree, although it will not be pushed inside the queue because his in degree hasn't become 0, but being maximized, it will be a depth of 3. Okay, here the depth is 1. Then I will remove it. The depth will become 2. I will remove it. The depth has become 3. I will remove it. The depth of this has become 4. I will have to maximize it. It will maximize to 4. Although not pushed inside Q because it still has an in degree of 1 with him. So it cannot be removed. Same way, I will try to come from here. It is a depth of 1. Then remove it. Then a depth of 2. Then remove it. Then a depth of 3. Remove it. Then ultimately a depth of 4. Again, by default, it was 1. I will maximize it, getting a value 4. Here, the depth was 1. I'll try to remove it, maximize it with the depth of 2, but already it's at its maximum. So what we found was, okay, the graph will look like this specific node has a depth of 4. This node has a depth of 2. Sorry, 4. Now, obviously, I told you one very sad fact that now you have to figure out the cycle length. This helped you to figure out the extension length as a form of depth. But now figure out the cycle length. How to do it? Simple. Just get one node. Let's say I will tell you firstly how to do it, like from here. Let's say I get any one node, which is, let's say, 0. Okay, so current node is 0, right? Then I will say, okay, in the very beginning, I will say, okay, remove this node. So remove this node. Okay, simply remove this. When I say remove this, his neighbor, I will say again, let's say if I remove all this, okay? Let's say if I remove all this, he was here, then I simply mention that the current will be this now. So this is my current node, let's say 1. But again, make sure that what is happening, the cycle length in the very beginning when you had just one node will be, let's say, 1. Again, let's say if you remove this, you can increase it then also, or you can, again, it's kind of a variation of how you implement it. The way how we have done it is simply, let's say if we had this in the very beginning, as soon as I take this specific node, I will put its in degree as 0. Maybe let's, I'm removing it from the corresponding data structure which I have, and then I will increase the cycle length. Then assign the corresponding new current node. Again, the current node is this one. This will become, removed. Again, to remove it, there are multiple ways. You can mark things visited. You can mark things with a, incorrect in degree value. There are multiple ways. We will mark it with the incorrect in degree value, because in degree value will tell us what all nodes are visited or not. Okay, just to use the data structures. Same way, if the one was visited, cycle length was 2, and now the current will become 2. Same way, when 2 will be visited, the cycle length will actually become 3. Now the next one will become 3. Same way, when 3 will be visited, cycle length will actually become 4, and this is also gone. Next one will become 4. Same way, when this is gone, cycle length will become 5. There is no next node, although there will be, which is 1, but 1 has in degree of 0, which means 1 is already visited. Then answer will stop. Cycle length achievable was 5. Obviously, I will have a condition. If the cycle length is 2, then make sure to do something else. I will tell you what something else is. But if it is not, then maximize or get the longest cycle in separate variable altogether. So this is a cycle length, and I will get this in a separate variable, which is longest cycle. And this is the exact same code which I actually did, that I went on to all the nodes. Firstly, I checked if it's in degree 0, which means it is already visited. When I say already visited, which means I already visited that when I was, reducing the branches, right? This is how what I did when I was reducing the branches. I was simply making the in degree as 0. So which means either it is reduced branches. And also this will also help me, because while I am actually reducing the current cycle by, taking the corresponding node, getting the increasing the cycle length, and assigning the current node to its neighbor, I'm also putting the in degree as 0. What this in degree here represent? Okay, it is visited. That is the reason I'm reusing in degree, just so as to put things as visited or not. Okay. Then when this portion is done, there's one just quick thing, that what if there is a cycle of length 2? No worries, cycle of length 2. Then I have this specific, obviously the same thing here also. In the very beginning, node 0, the like cycle length is 1, neighbor is 1. Then this is, let's say, gone, right? For like, then for 1, the neighbor is 0, cycle length is 2. Though so cycle length is 2. In that case, cycle length is 2. What did you realize? That cycle length is 2, which means I will have one node here, another node again, like not another node, but yeah, in the final case, one node, like your current will be pointing to the starting node, because it was the cycle length of length 2. Although current here is also pointing to starting node, from which I started off, but again, in general, it will be node which was here. So this is, let's say, one person. His neighbor will be the his neighbor will be the another person who is just beside him, and also because they are participating in a cycle of length 2, which means I should take in consideration their extensions. Their extensions are represented by 4 and 4. What this 4 means? This 4 means I have 3 neighbors and 1 themselves. Again, this 4 means I have 3 person and themselves. So I should technically add, if this is the person, this is his favorite person. So person depth, favorite person's depth is actually the neighbor. So person's depth and favorite person's depth, just simply adding it. Now you might say, Aryan, what is this adding? As I told you, if there are multiple components, in which you have multiple such, cycle of length 2, in that case I can add all of them. Like for example, I can have this also along with this, because I can attach their endpoints. That is the reason I'm simply keep on adding the corresponding cycle lengths, and ultimately maximizing that. Okay, is it sum of all components with extensions of cycle length 2, or simply the longest cycle in the entire graph? Cool. Let's see the code combinedly at one place. It is exactly as what I showed you in a dry run. Firstly, I have in degree 0 and depth of 1 initialized by default. Then I went on to all the nodes to actually put up their corresponding in degree based on the favorite person they had. Then I went on and said that, okay, get me all the nodes with the in degree of 0. This is required so as to start reducing extensions. So then I will try to reduce extensions. What I will do, until my queue is empty, which has these end nodes, I will grab out the front, I will find the neighbor node, and then I will increase or maximize its depth. Again, you remember why I'm maximizing it? Because I told you that as it is being, let's say if I go back, Yeah, as it is being maximized from some nodes, maybe the other person who is maximizing it doesn't maximize that much. That's the reason I'm maximizing my corresponding depth. Okay, now obviously when I maximize it, I'm making sure that I reduce in degree. This will also help me to, reach to a state where I only and only have cycles. So now I reach to a state where I only and only have cycles. To figure out what all nodes I've already visited, I will simply check if their in degree is 0, which means I have already visited them or I have already reduced them. In other case, I will simply go on and figure out that, okay, just try to reduce it. If the length is 2, make sure to add the person and the favorite person's depth into my cycle length, sorry, into my answer, which is, a cycle of length 2, the entire component sum with extensions, all that. I'll simply add in this variable. Or if it is a cycle of length more than 2, then I'll try to maximize the corresponding longest cycle length. And ultimately, maximum of this will be the answer. Because you are doing a simple DFS, or sorry, I should say simple BFS traversal. That is the reason time will be O of n. And again, because it's a simple BFS traversal, again, space will be O of n only. Again, this you can do it with the help of DFS also. But for this portion, it is much more beneficial to do it with the help of BFS because it is much more intuitive. Again, this is simple Khan's algorithm. Bye bye. Take care. I hope you guys got it. Again, this is kind of a inference, although not directly Khan's, but it is kind of an inference of how you can easily do it if you know Khan's. And again, if you don't know or if you have any confusion in the corresponding cycle portion, just go and watch this one video. You will get everything. Bye bye. Take care. And make sure if you like the video, please like it. The article with code in all the languages and with company tags and all the stuff will be on the website soon. So yeah, make sure to check it out. And again, it has everything, the corresponding system design syllabus, HLD, LLD, what all to cover, all the things you can find it here itself. Again, let's say for HLD also, like we have all the topics. Bye bye, take care.